Brazil for the 4 main LHC experiments. We start with Professor Marcelo Munhoz from the Universidade de São Paulo, who will represent and show the highlights for the ALICE collaboration in Brazil. So please.
Okay. Thank you, Antonio. Thank you, Ulisses, for the opportunity to speak here, for the invitation. So I'll try to be very in time. That's the requirement. And I'll show you a brief, very brief, of course, overview of the participation of Brazil in ALICE. I try to be very fair with all the groups, all the universities. So it's a lot of things, but I hope I can convince you that we have a very significant participation in ALICE. So first of all, since we have a broader audience, what is ALICE? ALICE is the only experiment in LHC that is optimized to study collisions of high energy nuclei. Of course, all the experiments do that, but ALICE was designed for that. And it has, as every experiment, has many subsystems, many detectors, and is not so large as ATLAS and CMS, as you see. 40 countries, 150 members more or less, and almost 2,000 members. So the goal of ALICE, of course, if we study if our focus is the high energy nuclei collision, our goals is to study the nuclear matter, the phase diagram of nuclear matter. We, of course, concentrate in one spot here when you have high temperature and low baryon density. And the idea is to probe the emergent QCD phenomena. So what kind of a solid state of strong interaction. So what kind of phenomena comes from when you look at a kind of large system that is driven by the strong interaction. And of course, one of the main players in this kind of studies is the quark-gluon plasma. So that state where you have the confined quark and gluons in a large volume. So I like very much this quotation from these people. So it's the simplest form of complex matter that we know of, most directly connected to the fundamental laws that govern all matter in the universe. So I think it's very kind of poetic. So in Brazil, we are 4 institutes. So University of São Paulo, where I'm from, Unicamp, Cristiane is from, you heard about her, UFABC, and Federal do Rio Grande do Sul is the other one. So we are dedicated to physics analysis and also instrumentation development. So we try to be present and develop work on both fronts. And in terms of size, we are 9 faculty, so more or less 2% of ALICE. And also in terms of PhD students, also around 2%. So I saw this morning Salvatore's presentation. I think this is like a magic number. Brazil is 2% of CERN, and we are 2% of ALICE. So how we do this study, how we study this strong interacting matter, how we do that. So we use heavy ion collisions. And the challenge here is the fact that, of course, if you, oops, go back a little bit. When you do this collision, you expect this quark-gluon plasma or this medium to be formed in the very beginning of the collision. And of course, since it's a very hot thing, it will expand and cool down very quickly. And then it hadronizes. You have a lot of inelastic scattering. You have a lot of elastic collisions. And then what you really measure in the detector in the end is we call freeze out, is just the last stage of this evolution. So what we need to do is to measure through the measurement of this final state to infer something that happened in the beginning, the properties of the medium, and so on. So it's 10 to minus 20 something. Yeah, it's very, very quick. So in a very simple way of putting it, we have 2 strategies, let's say, 2 big strategies. One is to look macroscopically to this event. So trying to measure the global observables at the freeze out, and from that, try to infer what happened in the beginning. And another way is to microscopic characterization. So we do a Rutherford-like study where you have some hard probes, some high energy probes that you expect it to traverse the medium. And so if you compare how it was in the beginning, somehow, and how it came out in the end, you can infer something about this medium. So, and of course, last but not least, we need to compare any measurement with proton-proton and proton-lead collisions to make sure that we are getting something new from these high-energy nuclear collisions. So in Brazil, one of the fronts, one of the studies that we do is the strangeness enhanced measurements. So the idea of strangeness enhancement is more or less the following. You expect from direct production of strange hadrons to be very suppressed. So if you have only hadronic collisions producing strangeness, you expect it to be suppressed because of many reasons. And the idea was put many years ago by these two gentlemen in the 80s, that if you have the QGP formation, you enhance the production of strangeness. You make it more easier to produce strange particles, mainly multi-strange particles. So this is a very nice signature or way to study this medium. So here is a very nice result. So if we look at this plot, this is just the yield of different strange hadrons to the number of pions as a function of the multiplicity of the collisions. So if here you have proton-proton and here you have heavy ion. So you see that is a very clear enhancement when you go to proton-proton to heavy ion. This is known for a long time. So the big contribution from the Brazilian teams, mainly no, all from Unicamp, is the study of the production of these hadrons as a function of multiplicity in proton-proton collisions. Then we see that is a very smooth transition from proton-proton mean bias to heavy ion collisions. So this was something surprising. As you see, was even the cover of a Nature Physics magazine. And so this increase with the multiplicity was really a paradigm shift in heavy ion physics. So because of course, if you believe that the plasma is formed only heavy ions and not in proton-proton, what's going on here? So that was really a fundamental contribution. And this studies is going on. So for the next steps, the group is trying to explore further this landscape of strangeness with new hadrons like the sigma 0. The idea is to explore isospin symmetry with this guy, and also with very advanced analysis techniques like machine learning and stuff to really see these rare hadrons. In the other front, in the microscopic view, we study heavy flavor hadrons, both open state and quarkonia. So the idea that these heavy quarks are produced in the very beginning of the collision through hard scattering. And so this is the thing that we would start to explore the medium. So we know how they are produced, is more or less under control with perturbative QCD. They do not change their flavor through the passage of the medium. And also, since they are heavier, it's more or less known how to calculate their transition through this medium. So it's a very nice probe. Also, we can look at quarkonium because the medium can screen the pairs, the CC bar, for instance, and then you expect a suppression. On the other hand, you expect a lot of production of CC bars, so we can have what we call regeneration. So it's a very complex dynamic that can bring information about the medium. And the way we look at these hadrons is just through their decay, hadronic or leptonic decay. So a very easy way or straight way to look at this phenomena is through this nuclear fragmentation function. It's just the ratio between the spectra in heavy ions divided by proton-proton, of course, normalized to the number of collisions you expect in heavy ions. So we did that in our group in Brazil, looking at electrons that come from the decay of heavy quarks. And so if we go look at this ratio as a function of centrality, so this is more peripheral collisions, we see that the ratio is very close to 1. If you go to a more central collision, you see that this ratio is less than 1, and in the most central is much less than 1. So this is a very clear sign that these quarks are really interacting with the medium and really bringing information about the medium. So now we need to understand better what kind of information it brings. And of course, one step very important to understand that is to look at proton-lead collisions to see if there is an effect of just because the nucleons are inside the nuclei, not just by themselves. And so we did that. This is Cristiani's work. The RP-lead, so it's the ratio in P-lead, and we see that it's compatible to 1. So really, what we see here is due to these new effects of the heavy ion collision. Okay, and then the next step in this area is to expand these studies with full jets, not just the leading particle, not just the hadron that carries this heavy flavor quark, but try to reconstruct the full jet of the fragmentation of these quarks. And the idea is to measure these jets tagged by or electrons that come from heavy flavor or directly from the mesons, and also jets tagged with J-psi, the quarkonium. So, and the idea is to not just to look at the jet by itself, not just the spectra, but also to explore the substructure of these observables. So we have a lot of observables, quantities that you can extract from the jets and then try to see how the structure of the jet itself changed because of the medium. So for the upgrade, now going to instrumentation. So well, people from, I guess, LHC knows that we are in the run 3 and we expect run 4, hopefully into 2030. Let's see. But in Alice, what we did, the main upgrade we did was for run 3. So we changed many things to reach a 50 kilohertz rate of collisions for lead-lead. So different new detectors were added. Important for us, or for this talk, is our participation in the TPC, that we work in the faster and triggerless readout front-end chip. And also people from Rio Grande do Sul, they worked in this Munhoz for the detector. So for the TPC, we developed the difference between, in this upgrade, we changed the way the charge are multiplied by the detector. So instead of multi-wire chamber, they put a jam system. So it's just foils of isolant material with conductors in both sides. So when you apply a potential here, you have an intense electric field that multiplies the charge. And we had to do, in order to use the system, we had to develop the new front-end chip. And then we called it a Sampa, just because it was done in São Paulo. And the good thing, and the challenge in this project was really to work with both analogic and digital functionalities in the chip and have a continuous readout in order to keep up with this rate. And we also have many studies with the aging of these jams. So Thiago is a professor at the University of São Paulo, is working on that. He's leading this work. So the idea is to study if these jams will be heavily damaged by radiation, and so trying to think about mitigations and things that you could avoid that. So he's using very innovative techniques to do that. For the MFT, that is a high-resolution silicon tracker forward, in the forward direction. So what the contribution from Brazil was the mechanical infrastructure, and also that was built in Rio Grande do Sul, Porto Alegre, and also the software that was developed by Rafael, also a former professor from the university. Okay, for run 4, we are involved in this forward calorimeter, the focal. And the idea of this calorimeter is to explore the small X parton structure of nucleons, and mainly nucleons in the nuclei. It's electromagnetic and hadronic calorimeter, also in forward region. And our contribution is in the electromagnetic part that is composed of layers of tungsten and silicon, 2 layers of silicon pixel and 18 layers of silicon pad. This is also being developed, worked in Rio Grande do Sul and São Paulo. So they have a very significant contribution to electronics of the pad detector and also for the detector control system. for Alice, for the future, so you heard already, but we have this proposal that we are putting in place, this Alice 3 upgrade that is aimed for run 5. Yeah, I'm finishing. So this will be the next generation heavy ion program. And this is just to let you know that this LHCC report that considers Alice 3 a unique detector for a heavy ion program in the future. And so this is a very innovative concept, very lightweight, all silicon tracker, retractable vertex detector, particle identification, and so on. And one highlight that I like to say here that you also heard already is the subconductor magnet that will be built for this detector, and this is being done in Brazil. So the design has already started in CNPEM. That took the lead of this part of the experiment. They have already started design, and now they are investigating the possibility to produce the cable here, the superconductor cable in Brazil, and then, of course, build the whole magnet here. And also, we are involved in these time of flight layers. So the idea is to build a silicon detector with 20 picosecond resolution. And this is a very nice also common project between Alice and Atlas in Brazil, because I think Marcelo will present. They are building the LGAD detectors, or they are qualifying the LGAD detectors for Atlas, and we are going to use the same infrastructure that was built for that in Alice. So this is the end. I hope I have convinced you that this, the QCD, the heavy ion program is a very nice way to study QCD matter. Alice is well positioned for that, and although we are a small fraction of the experiment, we have contributed significantly to the experiment, and the future is promising. That's it. Thank you. One minute.
Thanks a lot, Marcelo, for the very nice talk. We have time for one question. There is. Marcelo, so for focal, you're developing the sensors, or?
No, we are just we are working on the electronics, the front end chip, qualifying the electronics, and then we are going to help with this control system. But we are not working for the focal. We are not working with the sensor itself, only the electronics.
Thanks. So let's think again, Marcelo.